Hello everyone. Today I will talk about semiconductors. So semiconductors are materials whose electronic properties are intermediate between those of metals and insulators. And the magnitude of band gap of semiconductors lies between that of insulators and metals because today I'll discuss mostly about the band gaps, semiconductors in terms of band gaps. So the band gap of the semiconductors lies between that of insulators and metals. The interesting feature about semiconductors is that they are bipolar and the current is transported by charge carrier, that is the two charge carrier, that is the electrons and the holes. Of course, the resistance of semiconductor decreases with the increase of temperature and it has negative temperature coefficient of resistance. So of course, if the resistance decreases with the increase of temperatures, then its conductivity increases uh, with the increase of temperature, and which is very opposite to the conductivity of the metals, because in metals we have a lot of free electrons. So as we increase the temperature of metals, the vibration increases, which result in increase in the resistance of metal. So the resistivity of the conductivity decreases. So uh, we'll discuss the properties by the of semiconductors by their crystal structure, bonding characteristics, or their electronic energy bands. So first, I will discuss something about the band gaps of the metals and insulators and the semiconductors. So each allowed band gap was found to contain a limited number of energy levels. According to Pauli exclusion principle, each energy level must be occupied by no more than two electrons. So for example, if we take the example of copper, and which is a monovalent metal, and it means that it has one electron in the outermost shell. So below that one electron in the outermost shell, below that all the energy level of course will be filled. So for example, we have a take the example of 4s1 level, and we have a copper wire. So in that copper wire we have a million of electrons. So for example, these are the copper, all of the copper atom with a 4s1 level. So every level have one electron there, and below all below that level all the uh, levels are fulfilled. So when these electrons come together, they will form a band. So according to Pauli exclusion principle, no more than two electron will occupy the same band. So one electron spin up and spin down electron, then spin up and spin down electron. So in this way they will fill all these energy levels up to that level. This is known as the Fermi energy level. This is the highest energy level of the band. So so this band is known as the valence band, and above the valence band we have another band uh, which is known as which is called the conduction band. So for metals, the it's very easy to make a transition from valence band to conduction band. Even at room temperature, the electron jump from valence to conduction band. And sometimes we have two type of metals, two cases in metals. One, we have a fulfilled the valence band, or we have a overlap valence between valence and conduction band. So in metals, because we have a lot of free electrons, so there is a very small band gap between the valence band and the conduction band. So they of course this is the case, that is why the metals conduct electricity easily. But in the case of diamond or silicon, diamond, which is an insulator, and silicon, this is the semiconductor, it's very difficult or different. For insulator, here we see that the band gap is 5.4 electron volt, and silicon it's 1.1 electron volt. For semiconductors, the band gap, the typical semiconductor EG is the band gap is less than and equal to 1 electron volt. So mm, so this is the case for the semiconductors and insulators. So the monovalent metals such as the copper, silver, and gold have, of course, one electron in the outermost shell, and hence the corresponding energy band is only half filled in these metals because they are monovalent. On the other hand, the divalent metals such as beryllium, magnesium, and calcium have overlapping valence and conduction band. So the band structure of trivalent metals such as aluminium and gallium, etc., is similar to that of monovalent metals, and the tetravalent metals such as the carbon, diamond, silicon have even number, like four number of electron in the outermost shell, like divalent metals. The corresponding band is full, but unlike the divalent metals, there is no overlap of valence band with the conduction band in this case. However, as we go down the column from carbon to lead in this group in the periodic table, as we see here, the band gap of room temperature decreases in the order. So as a result, the diamond behave like a insulator. Mm, Diamond behave like insulator, and at tin and lead behave like a conductor, and then the silicon and germanium behave like a semiconductors. So this is all about the band gaps, and how the outermost shell, how the valence electrons behavior, which makes them the matter. So we have two types of semiconductors: intrinsic semiconductors, which are in the pure form, we can say, or extrinsic semiconductor, in which we doped the material. So intrinsic semiconductors are those semiconductors having energy gap of order of 1 electron volt, comparable to the thermal energies. Hence, the conduction process in these materials is achieved as a result of thermal excitation of electrons across the energy gaps. So if this is the valence band of the valence band of the intrinsic semiconductor, and this is the conduction band of the extrinsic semiconductors, then when at absolute zero, the valence band of the intrinsic semiconductor is completely filled. So that's why these at absolute zero, the intrinsic semiconductors are behave as the insulators. So as we increase the temperature from the absolute zero, the transition will occur, and then the electrons from the valence band jump to the conduction band, and the vacancy is created inside the valence band, which we call as a hole. So there are two type of intrinsic semiconductor, we can say that. In the elemental form, which are from group 4 of the periodic table, 4a of the periodic table, or compound form like group 3 5 or 4 4 or 4 6 of the periodic table. So these are the elemental compound form of the intrinsic semiconductors. If, in terms of conductivity of the intrinsic semiconductor, we know that the current density is equal to sigma into E, and sigma is the conductivity of the conductivity, and E is the electric field. So if we divide E at from the both sides of the equation, then this term will express the mobility of the electrons. So conductivity of the conductivity of the semiconductors depend on the n is the number of the charge carrier per unit volume, and then the conductivity depend on the number of the charge carrier and the mobility of the electrons, or in this case we have electrons and holes, because in intrinsic semiconductors we have equal number of electrons with holes. So we can equate both electron and holes, and we can say that this term is equal to Ni, and we got this kind of equation for the conductivity of intrinsic semiconductor, and I will explain this equation further in the later slides. Okay. uh, Come to the extrinsic semiconductors. The real semiconductor grown in labs are always contain impurity, and then which create their own energy level called the impurity level. These level occupy position anywhere in the allowed and forbidden bands of the semiconductors. So according to our needs, we intentionally introduce impurities to the host materials, and the resultant properties depend on the type of impurities we introduce. So normally a few part per million of suitable impurity materials added to the host materials during the growth of the semiconductor crystals. So we get the N type or the P type of the intrinsic semiconductor by the addition of these impurities from group 3 or group 5 of the periodic table. So first we will discuss the N type of semiconductors. N type, we can N is for, we can learn this that N is from, or we can remember this that the N is from the negative. So it means that we have a more number of electrons in these type of semiconductors. So the intrinsic semiconductors drop when the intrinsic semiconductors like silicon is dropped with the pentavalent impurities are then they are called the N type of semiconductors. And the energy level of the fifth electron is called the donor level. Of course, the donor level is very close to the bottom of the conduction band, and most of the donor level electrons are excited into the conduction band at room temperature, and they become the majority carriers. Hence, in N-type semiconductor, electrons are the majority carriers, and holes will be the minority carriers. So, if this diagram is the schematic of the N-type semiconductors, in which when we dop the impurity atom, which here is phosphorid, which is pentavalent, have 5 electrons in their valence band. So we have a free electron for conduction. So because the 4 of electrons are will be covalently bonded with the silicons, and we will have an extra electrons, a free electron, which will take part in the conduction. So this type of materials are known as N type of semiconductors. So here the Fermi level is very which is the donor level. The Fermi level is actually the impurity level of the uh, of the doped material. So here, because we have doped a pentavalent material, so it have a extra number of electrons. So the this impurity level or the Fermi level is very close to the conduction band. So at very low energy, electrons from this donor level go to the conduction band, take part in the conduction, and the current will start in the material. So because of the doped material, impurity level or the highest energy levels come close to the conduction band. So this is the schematic of the energy band gap diagram of the N-type semiconductor. Then if we go toward the P-type semiconductors, in the P-type semiconductors, when a trivalent element such as aluminium, gallium, or indium have been doped into the silicon, then because they have 3 electrons in their outermost shell, then they need one more electron to complete their bondings. So this electron may be supplied by silicon, thereby creating a vacancy, and electron side or hole are created inside the material. So indium accepts one extra electron. The energy level of this impurity atom is called the acceptor level, and this acceptor level is just like above the valence band. Now we have in the N-type semiconductor we have a donor level. Impurity level is the donor level, and in P-type semiconductor we have the impurity level, which is the acceptor level. So these type of trivalent impurities are called the acceptor impurities, and the semiconductor doped the acceptor impurities are called P-type semiconductors. So we have this schematic of P-type semiconductors, in which indium is doped with silicon, and then 3 of the electrons, valence electrons of the indium have been covalently bonded with the silicon, and one hole is left. And here this is the impurity level, which is the acceptor level of the indium, and then which it is very close to the valence band, and then at very low temperature the electron from the valence band jump to this acceptor level and create a vacancy in the valence band, and that's how the conduction gets started. So this we already talked about this equation before, but this equation show the conductivity of the intrinsic semiconductors. So we will now see how the charge carrier concentration, charge carrier per unit volume. This is the charge carrier concentration per unit volume. How the this charge carrier concentration varies from intrinsic semiconductor and to extrinsic semiconductors as a function of temperature, we can say that. So for here I have some graphs here. So for if we plot the charge carrier concentration with respect to temperature, we see that for this is the behavior for intrinsic semiconductor, and this I will plot this behavior for the intrinsic semiconductor, and this is for the extrinsic semiconductors. So we will see that at very low temperature there is there is no charge carriers, or there is no because of there is no charge carrier, or there are no electrons which are taking part in the electronic transitions, because the temperature is very low and the electrons are the at the freeze out level, so there is no transitions. But once but once we cross the certain threshold temperature, that there is enough energy that the electron from the donor level comes to the valence band, or the electrons from the valence band come to the acceptor level. So for example, we have this kind of intrinsic semiconductor in which we have a here for n type we have a donor level, and for a p type we have a here the acceptor level. So it means that, and these impurities which we have doped is in the finite number, or we can say that these impurities we are doped here are in a very specific number. Or of course once the carrier concentration cross the certain transition temperature, they will saturate and they goes off, and but it will stay constant but the conduction process stay constant for a long amount of time, because of this because of this limited number of the carriers in or dopants in the extrinsic or intrinsic semiconductors, N or P types. But after at a high temperature, this goes off, and it will the conduction the charge carrier concentration abruptly increases at very high temperature. So for if we talk about the intrinsic semiconductors, we say that there is a very large band gap, more than the extrinsic semiconductors. At low temperatures, the charge carrier will not behave to the low temperature, but at when they will cross the certain temperature, the transition will start, and it will goes off. So this is how the extrinsic and intrinsic semiconductors behave with the increase of the temperature. It is very consistent with the energy band diagrams which we looked before. So if we want to, or if we wish to look to see the how the mobility varies with the charge carrier concentration, we see that this is the log of mu term. For example, is -3, -2 log and -1. We see that for the electrons, mobility for electron and hole, with the increase of charge carrier concentration per unit volume, the mobility decreases, and also with the increase of temperature, the mobility of the charge carrier of the electrons, or we can say the hole, it will also decreases. So when we talk about the this equation, come to that equation which we have discussed before, that conductivity is equal to Ne mu. It depend on the conductivity, depend on the mobility and the number of the charge carrier per unit volume. So we now see that the mobility decreases with the increase of charge carrier concentration, also with the temperature. So it means at a high temperature, this term will goes down for the semiconductors, but the charge carrier will go up. So as a result, the conductivity of the semiconductor will go up. So it means that the the number of the charge carrier concentration which goes up are higher in number than the mobilities, the number of the mobilities which is going down. So that's why as, the semiconductor conductors conductivity with respect to with the temperature, they will increases. So but for the conductors, we will say that for if conductors n e mu e, for the conductors this mobility terms will also decrease, so that we say that the conductivity of the metals or the conductors goes down. So um, uh, the general behavior of this conductivity for semiconductors and metals, for metals and for semiconductors, it's we can say the same. But the term which differentiate between the semiconductors or the conductors and mobility carriers or the charge carrier. So in general we can say that the generally and broadly speaking, we always say that the conductivity of the conductor is more than the semiconductor, of course, because we have a large number of charge carriers which are more than the semiconductors, which are two more than in the semiconductors. But at high temperatures, this mm, uh, this terms goes down, but with the increase of temperature, this comes for the semiconductor, this term goes up. So this is how the mobility or the charge carrier differentiate between the semiconductors and the conductors or the metal.